Right. Okay. Welcome back to the next in the series, and I'll just want to remind you that we've had a look at vibrational spectra, and we've had a look at rotational spectra. And before I continue, I just want you to remember that when you work with rotational spectra, that these the distances between the levels go 0 to 6, 12, 20 HCB, and that works nicely because then when you have the jump, and that jump is 2 and that jump is 4, the difference is 2 HCB, or it's 2B in wave numbers. But if you go back to the energies levels go 0 to 6, 12, 20. So please remember these relative positions of those energy levels, because they're going to become very important when we look at more complex spectra that we're about to do. So just a reminder, when you look at rotational spectra, what we do is we've got, just hang on, what we need to do for the molecule is know what its reduced mass is. From the actual spectra itself, we know that the distance between the bands is 2b, 2 times the rotational constant, so we can get the rotational constant, so we can get the moment of inertia. And if you've got the reduced mass and the moment of inertia, then you can calculate the bond length. Right, so the more complex spectra that I want to look at are when you've got vibrational and rotational levels overlaid with each other. Now, this is going to take a little bit of explaining, so just please be patient. Firstly of all, this potential well, you'll notice, is the harmonic potential well. It's not a Morse potential, but I'm using that for simplicity. And of course, remember, your vibrational energy levels in a harmonic potential are equally spaced together. But we said that in the real case, for real atoms with the Morse potential, the first jump really matches quite well between harmonic and the Morse potential. So that's what I've got here. So down here is your first vibrational energy level, right at the bottom here. And over here is, so that's your 0 point vibrational energy. So that's the lowest point you could have. And here's your first vibrational energy level. So there's vibrational energy level 0 and vibrational energy level 1. But of course, a molecule doesn't have to just vibrate. It can rotate at the same time, and those rotations are quantized, and so you will have various rotational energy levels that are superimposed. So you can see that if a molecule is right here, it's in vibrational energy level 0 and rotational energy 0. If it's at the next one up, it's in vibrational energy level number 0 and rotational energy level number 1. If the molecule's at this energy level, it's got the lowest possible vibrational energy. It's at energy level 0 point, but its rotational energy level is at energy level number 6. And similarly, when you go to the next vibrational energy level, you've got your possible rotations that you have over there. So you've got lots and lots of possibilities between your lowest vibrational level and your next vibrational level, because it can have different energies of rotation as well. So that's quite an interesting situation. But I want you to remember from the rotational energy levels that, of course, the distance between 0 and 1 is 2b in wave numbers, or 2 HCB in energy, and between at energy level 0, it's 0, energy level 1, it's 2 HCB, then it's 6, and then what was it, 10, 12, and then 20, so it's going up. So the difference between these levels is always 2 HCB, but it's going up 0 to 4, 10, and so on. So don't forget these energy levels over here. Don't forget that 0 to 6, sorry, my apologies, 0 to 6, 12, and 20. Don't forget those. So 0 to 6, 12, and 20. Don't forget those differences that are there. Because when we come to the spectra, we see when you're allowed to absorb energy and jump between these levels, you get quite an interesting spectrum that looks like this. So this is a combination of vibrational rotational spectra. I just want to warn you that we are in a much more energetic region of the spectrum than we were for simply the rotational energy levels, because you can see that these are the rotational energy levels. You can see the jump between these is very small. But of course, now if you've got to jump to a different vibrational energy level, you've got a lot more energy being exchanged for those jumps. So please note that we're in a different region of the spectrum. We're giving it enough energy to jump right out of the one vibrational energy level to the other vibrational energy level. But what we have are different branches, there are different ways that jump can occur. And there are some selection rules, is that your vibrations must change by 1. In vibrational rotational spectrum, your vibrations change by 1. So it's going from one vibration to another. But your rotational energy can either drop or it can go up +1. So let me explain what that means so you can see. Have a look over here. It's going from vibrational 0 to vibrational 1. That's fine. All of these are going from vibrational 0 to vibrational 1. But look at the rotation here. This particular line is going from rotation 1 to rotation 0. So the change is going down. So the rotational energy level is dropping as it goes up there. But have a look at this one. It's going from rotational energy 0 to rotational energy level number 1. So that's interesting as well. So we've got a change in those rotational energy levels there. And those are the P branches and the R branches. And often in diatomic systems is forbidden the Q branch, where you've got no change in rotation, where you go from vibration 0 to vibration 1. But you can see it's going from energy level 0 for rotation to energy level 0 for rotation, energy level 1 for rotation to energy level 1, and so on. So the Q branch is not seen. And in this particular spectrum we're seeing here, we're not seeing the Q branch, we're seeing the P branch, and we're seeing the R branch. So just to give you, just to warn you, as you look here, see this jump here going from 0 to 1. I hope that you can see that these lines are getting steadily longer. And as they get steadily longer, the energy is getting greater and greater, so that on the spectrum you'll see the first line over here is the left-hand one on this bunch here, and they're going steadily greater and greater and greater and greater in energy as you go from left to right. Now here, I hope you can see that as you go from left to right, these lines are getting steadily shorter. The jumps are getting steadily shorter. So this is the biggest energy jump over here, and they get steadily shorter as you go towards the left. So this is quite interesting. So the question is, what on earth can we do with the vibrational rotational spectra? We don't have this nice little jump going from 0 to 1, 1 to 2, 2 to 3, that we could say that the difference is 2b. And of course, because we know the difference is 2b, then we can work out what the moment of inertia is and the bond length is. We don't have that. It's now going totally out of one energy level for vibration to another one. Could we ever get back to the 2b difference that we had before? So that is interesting. So let's have a look at a particular problem. So I just need to get to, there we go. So let's go to that. Right, so here's an example. And the example is with this CN diatomic system. And this is what the vibrational rotational spectrum looks like for the CN. And I've got some different wave numbers here for different bands on this vibrational rotational spectrum. So that's quite interesting. So what we have is this P branch are these jumps over here, and this R branch is those jumps over there. And the question is, from these, we can't directly find out what 2B is, but if we careful about our choices, if we're very careful about what we compare with each other, we might be able to extract out what B is, what the rotational constant is, and be able to work out what the bond length for Cn is in this case. Of course, in all these calculations, we need a reduced mass. And so we can look up what the masses are of carbon-12 and nitrogen-14. And if we get those masses, we can calculate the reduced mass for the system. And then we've got what we need to calculate the bond length for the system. So I want you to look very carefully over here. So in the first case, on the left-hand side, I want you to notice that I've ignored the largest energy level, and I've gone for the second one. And on the right-hand side, on this side, I want you to notice that I'm ignoring the second one and I'm going for the first. Okay, because on the left-hand side, the largest energy jump goes from energy 1 to energy 0, and the second one goes from energy 2 to energy 1. And I'm interested in this energy level 1 up here. So if I take energy level 1 as a reference, and then I find on the higher energy state what's going to energy level 1, which is this highest energy, that's also to energy level 1. Can you see these two start at the same point, but as you drop down, they end up at different points. So the band at 2061 is going from 1 down to 2, and the band at 2072 is going from 1 down to 0, which means that the difference between these two is something definite down here. Now remember, I wanted you to remember that we've got 0 and then 2 HCB and 6 HCB over here. So if you compare these two, it's dropping down exactly 6 HCB over here, which means in terms of wave numbers, we've got 6 times the rotational constant in terms of wave numbers if we compare these two bands. So just look carefully at the bands. Can you see at the top, they remain constant. At the bottom, they go to energy level 2 and 0. And if we went back to our graph paper, our rotational graph paper, the distance between level 0 and level 2 is 6. So there's a difference of 6B in terms of that difference over there. So this is a case where we're not going to say that the difference in bands is 2B. We've got to be very careful about our choice of bands that we choose, but if we're very careful about choosing the right bands, then we can choose two that have a difference of exactly 6. We could work the other way. Can you see the other band that we're not working with? You can see over here, they're starting at level 1, and they're both starting at level 1, but the difference that they end up is between level 0 and level 2. So if we chose those two bands, we would also get 6B there. Be careful though. The rotational constant is dependent on bond length. So be careful. Is it right to assume that our bond length at an upper vibrational level is the same as at a lower? That might be quite a wide assumption to make. So the question is, how do you know what jumps they are making just by looking at the diagram? If I understand your question correctly, are you saying how can we be certain that we're relating these spectra to the exact jumps that we're seeing here? Is that what's being asked?
Yeah, and just like how we make the choice.
How you make choice. Okay. So the experimental observation is that these are the jumps that are happening. So, but to make the choice, what I want to do, you see, what I want to do is I want to find two jumps that start at the same level. So I either choose this one starting at 1 and this one starting at 1 and choose those two, which means I can calculate the difference up here. Or I can start this one, compare this one starting at 1 and this one starting at 1 and compare the difference at the bottom. That's how I'm choosing them. Now, in terms of the spectrum here, the highest energy that you got on the right here will always be from 1 to 0. It's the biggest distance you can possibly have on the left-hand side. And the lowest one here, the left-handmost one here, is always the smallest jump here, which is always from 0 to 1. So if I can go back just a slide, remember that on this side, that these lines, this is the shortest line that you can have here, and these lines are all getting longer and longer. And this here is the longest line you've got, and these lines are all getting shorter and shorter. So we know that the longest line here, the highest energy jump, must be the highest energy jump here, and the lowest energy jump here must be the lowest on that. Does that answer your question?
Yes, thank you.
Right, so my apologies, that shouldn't occur. So let's go back here. I'm not going to do matrices, apologies for showing that. So what we've got here is the difference between these two wave numbers is 6b, which means that we can do a calculation. We can just take them apart and we know that it's 6b, and so we can get that as wave number. From that, we know what the rotational constant is 188.23 per meter, which means that we can calculate the moment of inertia. If we've got the reduced mass of the C1214N, use accurate masses for that. You'll get the reduced mass is 1.07 times 10 to the minus 26 kilograms. And so you can still, in this, you can still get the bond length. You don't need a pure rotational spectrum to get the bond length. You can use these as long as you are very, very careful about which bands you choose and make sure that they match at least at one point here from energy level 1, and see what the difference is down here. And you will be able to get your bond length at the end. Okay, so I prefer using the pure rotational spectra because if you've got pure rotational spectra, the difference is 2b. You divide by 2, you get b. But if you don't have it available, if you've got vibrational rotational spectrum, yes, it's more complicated. It takes a little bit more effort to try and find out what's going on, but you can still get the bond length from that. So I think the biggest take-home message on this as well, the point that I want to make on this is that your spectra, the moment you have more than one option available to you, like you've got your rotation and vibration together, your spectra become more complicated. Okay, let's go back to the slides. And let's go back here. So just note that that's how vibrational spectra work. Okay. Now, I suppose with the exception of a particle moving on a surface of a sphere, we've only been using the Schrodinger wave equation in one dimension. So that's the Schrodinger wave equation in one dimension. But I just want to alert you to the fact that the three-dimensional Schrodinger wave equation is extremely useful. And the first place as a chemist where it's extremely useful is in the context of a hydrogen atom. Please don't worry, we're not going to try and get into the wave function. In actually solving for the wave function, I'll present the results for the three-dimensional Schrodinger wave equation. But the results are very useful. And don't forget that this is always an eigenvalue equation. So the wave functions are eigenvalues of a three-dimensional wave equation. Okay, sorry, I missed a question on the rotational spectrum. And the question I got, is it always 6b? Well, it will be 6b if you choose a constant level, because you can imagine that if you're going from level 1, if you choose level 1, you've got to go to level 0 or 2. So if you're going from level 1, it's always to 0 or 2. And if you take the difference between level 0 and 2, it's always 6b. Okay, so if you're taking the, if you are looking at the least energetic of the R branch and the most energetic of the P branch, if you are at those two regions, it will be 6b. But maybe always related to draw this diagram and then say if you were comparing, for instance, level 5 with something else, it might not be 6b at the end. Okay, I hope that answers that question. Okay, right. So in the hydrogen atom, the only way to find out how this electron is moving around the nucleus is to use the three-dimensional Schrodinger wave equation. So already I'll just alert you that it is much more complicated. Now we've got a three-dimensional del squared operator instead of a d2 by dx squared. So it's far more complicated from that respect, but it's even worse than that because we don't even have this nice, you might recognize this e squared over 4 pi epsilon naught r is a Coulombic relation, and the electron and the proton have the same charge, although it's opposite, and of course that's why we have a negative there. So this is just a Coulombic. We don't simply have a Coulombic potential for that electron to move in. If that electron has got more, if it's got some angular momentum, you could maybe imagine that that angular momentum is pulling it away from the nucleus. And so Coulombic potential would look like this. But if you have a Coulombic potential with this angular momentum, you'll find that the potential that the electron is seeing is more like that rather than being pulled directly to the nucleus. So the form of the V part of the Schrodinger equation is quite complicated, and so it's a difficult problem to solve in the terms of a hydrogen atom. But it is possible to solve the Schrodinger wave equation exactly, and to get exact wave functions out of it, and these are extremely useful to us. So the solution to the Schrodinger wave equation ends up with these wave functions psi, and the psi are quite interesting because they can be represented as a radial component and an angular component. So the angular component really tells us about the shape of the wave function in space. So it's the shape really of the orbital, and the radial is telling us how it varies as you go away from the nucleus. So of course, our psi, of course, are simply our orbitals. The answers to the Schrodinger wave equation in terms of that are orbitals. And of course, if you fit them back into the Schrodinger wave equation, you can get the energies, the relative energies of those. But let's just have a look at the radial part, not the angular part of the orbitals as they come out. And you'll see that for a 1s, it's really quite simple. Here's the nucleus is at 0, and so you can imagine it's the same on the other side. It extends out to the other side as well. But of course, the wave function is really high, close to the nucleus, the radial, and as you move away, it drops down quite nicely. So that's as we expect. We expect electrons to be localized around a nucleus, and that as you get further away, you've got less chance of encountering that electron. But of course, it's as you get to higher energy levels, as you get to, as you include different quantum numbers in, you'll find that the 2s and the 3s are more complicated than the 1s in terms of how they vary going away from the nucleus. And of course, the p's are entirely different. But I hope you see that at the lower energy levels, it's far simpler. The higher the energy level, if you get to energy level 3, you're starting to see these complex radial distributions as you move away from the center of the atom. Okay, so just to show you, of course, if we want to know the density, we've got a square sign. So I've taken the previous slide and I've squared it. So at every point I've squared it. And so psi squared doesn't seem to have changed much. So for a 1s, you've got a high probability density close to the nucleus, and it gets lower. It's a cloud that gets thinner and thinner as you go around. But of course, it's interesting with the 2s orbital, you will see that you've got, of course, close to the nucleus, you've got a high density, but there's a region where you have a very low or zero probability density. There's a node, and then of course that increases and then decreases as you go around. So you can see that the 2s is more complex in terms of its probability density than the 1s. And similarly, the 3s, you will find there are two nodes. There are two places where it drops to zero as you go out from the center of the nucleus. So that is really interesting. So just note that you, from the solution, you have this radial and the angular parts to the wave function. And of course, there are three quantum numbers that you're already familiar with. N is the principal quantum number, and that really, the energy is dependent on that. The energy is not dependent on the others. And then, of course, you've got the angular momentum quantum number and the magnetic quantum number. But of course, it leads to degeneracy. So you'll see that if you're at energy level number 2, you end up with two wave functions that have exactly the same energy. So your 2s and your 2p have exactly the same degeneracy. So it's twofold degenerate. At level 3, you've got SP and D that all have exactly the same energy. But of course, my apologies, there are many different, so at NS3, you've got one of the S, you've got 3 of those, and you've got 5 of those. So apologies, that will be fourfold degenerate. There are actually 4 different things going on there. And over here, you've got 9 things going on here, so it's 9-fold degenerate. So the energy depends only on N, but please bear in mind that these results are only for a single electron atom. In our case, we've worked with hydrogen, so we haven't placed any other electrons in this atom. We're ending up with the energy is dependent on N, and of course we've got different possibilities. So we've got 3 different p orbitals there, and the s orbital there. So there are 4 different possibilities there. You've got s orbitals here, 3 possible p orbitals, 5 possible d. So there are 9 possibilities there. It's 9-fold degenerate at that level. So one other interesting thing to note is that there are selection rules for this, and the selection rules really say that you can jump in a hydrogen atom, you can jump from any energy level that's greater than 0. So you take a hydrogen atom and you shine light at it, or you get the emission spectra from a hydrogen atom, then what happens with the emission spectra is that with the emission spectra, you can jump from any energy level down to any other energy level, but your angular momentum number must change by 1. So you can't drop from an S to an S in these selection rules, and you cannot drop. Hang on, there's someone drawing. um, I can see someone's writing there. Please pause for a moment on that, unless there's a question. And so your angular, you can jump from P to S or D to S, and of course your delta ML can be 0 or plus or minus 1 as you drop down. So just be aware that there are selection rules. There are rules that you can't have any drop in that. Okay, just there we go. Right. So if we have it now look at the radial, I mean at the angular part of a wave function, we looked at the radial, and we've seen the radial goes through these nodes as you go outside. But let's look at the angular. Let's see what the shape looks like over here. And so look at the, I can't, please, whoever's done that, can you please remove that annotation? Okay. So when we look at the angular part of it, we know that the s orbitals, the wave functions we get from s orbitals, are all spherical. And of course, they get larger in terms of radial as you get further away. In terms of radial, you can see the detail as you move from the center outward. I just want you to note that, of course, this isn't psi squared. This isn't the probability density. So if you look carefully, you'll notice the positive and negative aspects of a wave function coming through. Those are extremely important that we have, because they might not be important in terms of how we calculate the density, because we square everything, but it's really important with how orbitals interact with each other. So that positive and negative aspects of the wave function are very, very important. Okay, so just hang on. So with s orbitals, what we have is the radial function goes, of course, like that. I showed you this part of it, but of course it's symmetrical about the atom. Okay. Right, with p orbitals, we've got an interesting situation, is that there are three possibilities where your ML is 0 or plus or minus 1 with that. It's interesting that when you solve a Schrodinger wave equation, you don't automatically get these three coming out. You get, for ML is 0, it comes out beautifully, but you end up with two other solutions that are not stationary and move. And so what you do is you take those two other solutions in a linear combination to get some orbitals that are now stationary in space. And so you'll end up with ML plus, so these two are linear combinations of ML that's plus or minus 1, so that we've got our familiar p orbitals that stand out at your x and y and z coordinates. Okay, note that your radial function is becoming more complex as you go out, and so of course at n is 3, the wave function is much more complex as you go. Note also the positive and negative aspects to it. So let's go back from the angular part of a wave function to just looking at the radial, and you'll notice that on one side of the nucleus is negative, the other side is positive, and that's why it's been drawn as blue and red. Okay. Now, D functions are only from n is 3 up, and you'll see that as the energy level goes up, you'll see they become more complex. But of course, ML is equal to 0 comes out really nicely from the Schrodinger wave equation, but ML is plus or minus 1. We have to combine those to get these two. We have to get a linear combination, two linear combinations out of those two, to get two that are stationary. And same, we have to get two combinations out of ML's plus minus 2 to get stationary orbitals, which is what we see in terms of, that's what we're familiar with in terms of d orbitals. Okay. And finally, other solutions that we get out of that are the F orbitals. And again, we have to be very careful with ML is plus minus 3, ML is plus minus 2, ML is plus or minus 1, and making combinations, linear combinations to get stationary waves so that we've got a set of stationary waves for our representation for F orbitals. So this is quite interesting. This is if we solve the three-dimensional Schrodinger wave equation in the context of a hydrogen atom, the answer are wave functions, and those wave functions are our orbitals. And those orbitals make chemical sense to us. We have already, in passive chemistry, we've been looking at orbitals and how they affect and how they help to describe reactivity of systems. It's interesting as well that you can only solve the Schrodinger wave equation exactly for an atom that has one electron. So now this then supplies us with questions. We, as chemists, we're interested in molecules. So the question is, how on earth can we deal with molecules? So important thing here is that if we go back and we have the three-dimensional Schrodinger wave equation, here's the three-dimensional Schrodinger wave equation with its complex potential that fits into that, then our solutions are all of these wave functions coming out here that have both an angular part and a radial part. Okay. Right. In this lecture, there may be questions, and I know there was certainly one question that I missed. So the question was, do we have to know those diagrams? So the question is, which diagrams? Is this in terms of rotational energy levels, or is it in context of solving Schrodinger wave equation for the hydrogen atom?
Both the probability density of the different orbitals with the 1s and then 2s, 2p.
Okay. Yeah. So please, so in terms of, I'm sure you know what the angular shapes are of these orbitals. So I'm absolutely certain you know those shapes. So question is, well, what else? I certainly want you to know the radial function for 1s. That's straightforward. I do want you to know that because that becomes really important when we look at modeling. And I want you to know in terms of the radial for others, I want you to be aware that the S orbit, the 2s, has this region of zero density in it. So it has this fine structure. I want you to know that. But in terms of being able to draw these, I'd like you to recognize them more than to be able to reproduce them from scratch. Does that answer your question?
Yes, thank you.
Okay. Are there any other questions before I sign off? Okay, right, then we'll carry on with this. Please, can we explain degeneracy? So just quickly, degeneracy comes up in many cases. So even in rotational energy levels, there is degeneracy present. Degeneracy is really about different solutions having the same energy. So you can imagine that at rotational energy levels, that if you've got something rotating clockwise, you can have something rotating anti-clockwise that has exactly the same energy. So what we have is this word that describes the situation is that those two are degenerate. It means that those two solutions, the clockwise and the anti-clockwise, have exactly the same energy. Right. Now, if we're looking at the hydrogen atom, if we're looking at the electronic energy levels, then the question is that how many answers, how many solutions to the wave function do we have that fit for energy levels 1? And the answer is we only got 1. So it's one-fold degenerate. But the moment you're at energy level number 2, at principal quantum number 2, then you've got a choice of angular momentum quantum number 0 or 1. So you've got different possibilities creeping in. So already you've got 2 possibilities that have the same energy. But of course, for L is equal to 1, you've got the possibilities of ML is 0 plus or minus 1. So at energy level 2, you've got 4 solutions that have exactly the same energy. And the 4 solutions are the 1s, the 2px, the 2py, and the 2pz. So all 4 of those have the same energy, so it's 4-fold degenerate. So the word to describe that is it's 4-fold degenerate. And if you go to energy level number 3 and you have a look at the possibilities, at that exact energy, you'll find that there are 9 solutions that have exactly that energy. The 3s, the 3px, 3py, 3pz, and then of course the 3d orbitals, there are 5 of them. And so you've got a total of 9, it's 9-fold degenerate. Does that answer that question?
Yes, thank you.
Are there any other questions? Okay, so if there are no further questions, as always, my email is open, and so you can ask questions throughout the day, and then we'll meet again at 11 o'clock tomorrow.